Well, hello everybody, and welcome back to 351. I have uploaded videos of I'm ready to begin if that's okay. I'm sorry. Welcome to 351. I have uploaded videos, answers to questions from the exam. You should now be able to go in on exam 2 and see your items missed, what your responses were, what the correct answers are. I'm trying a new thing to make the videos accessible to you, but only to those who have taken the test. I've embedded YouTube videos for each question as feedback to each question. It appears to be working for questions 1 through 16. For an inexplicable reason, someone has found that it is not yet working for 17 through 25. I have no idea what's going on, but I will check it and make sure that you have the ability to see that. It probably will take me, it'll be sometime later this afternoon that goes live. So if I can't get it to work, I'll just make them visible to everybody on YouTube and go on from there. So, and the other thing is that I've I've sent out a link to a Google Sheet with times that you can meet one-on-one with me via Zoom. I think it filled up for tomorrow and Friday fairly quickly, so I'll make more time available on Monday and perhaps Tuesday. First time around for exam 1, there weren't a whole lot of takers, so I didn't know whether or not to make enough time available, but where there's demand, we must increase the supply. Let's go ahead. I think we'll probably finish up with 7 and 8, probably on Friday. So I'm going to move the due date for study guide for 7 and 8 till after Friday. Today we're going to talk about the stereo and regiochemical consequences of the E2 reaction. And what we say for regiochemistry for the E2 reaction will actually apply for the E1 reaction as well. Stereochemical issues have to do with stereoisomers, the potential for stereoisomeric products. Regiochemical issues have to do with regioisomers. What are regioisomers? That's another word for constitutional isomers. I don't like that word because they're too complicated and sound political somehow. So instead, we just mean different connectivity. I mean, what is a non-constitutional isomer, and can you be declared unconstitutional? And so what do I mean by this? Well, let's look at this molecule to begin with. And this is a chiral secondary alkyl halide. Let's just suppose for the time being that we're going to use a base like tert butoxide. Often potassium's the counterion. Doesn't matter. This is a strong base or a good base, but it's a weak nucleophile because of sterics. It is too large to attack alpha carbons, and instead it can do elimination chemistry. So under these conditions, we would say, okay, the reaction's going to be E2. All right, well, now we're going to be looking for beta protons. So let's identify them. We have a couple here. Maybe A and B on beta carbon purple. And then we have 3 other ones on blue beta carbon. Now, it's pretty easy to see how there's not actually 3 different beta protons on blue beta carbon. We need to give it a number so that I don't have to say the color every time I mention it. Beta 1 has 3 identical protons. On a methyl group, you can spin around that carbon-carbon bond so that at any point, any of those protons could be anti to the leaving group. it turns out you might think that that is the same for protons A and B, but we're going to see that protons A and B are actually different, and removing one versus the other leads to different products. Let's draw, though, the product that comes from removing a proton from beta 1. That's going to have the following connectivity: a double bond between what used to be the alpha carbon and beta 1, and then you've still got protons HA and HB hanging out unreactive on the adjacent carbon. A couple of terms about alkenes that might be useful to you. We will sometimes refer to alkenes as olefins because it's easier to say than alkene. Too much ease and sounds funny. Sounds too nasally. Olefin is easier, rolls off the tongue. This olefin is what we're going to call monosubstituted. And the reason it's monosubstituted is the two carbons involved in the double bond total are only bonded to one non-hydrogen thing, and the other three are hydrogens. Okay? The calling things mono, di, and so on substituted is all relative to ethylene, which has 4 hydrogens attached to the 2 carbons of the double bond, and which we call unsubstituted. So if we replace one of those with an alkyl group, it's a monosubstituted alkene. If we replace 2, disubstituted, tri, tetra. Right. Oh, and in terms of talking about the carbons of a double bond, the carbons that participate directly in the double bond have a particular name that chemists use, and it can be useful to, instead of me saying that carbon right there, comma, the one that's involved in the double bond, period, I can just say the vinyl carbon. Vinyl carbons are ones that are involved in the carbon-carbon double bond. Carbons that are adjacent to the double bond we will call allyl carbons. Don't know why, that's just tradition. So all of that is just so we can have a sensible discussion. Those obviously aren't terms you need to memorize, but you may need to refer back to them to follow along with what we're going to say. All right, let's go back to the purple protons. And I want to demonstrate to you that these 2 protons are actually different from each other. Now, usually you've looked at a molecule like this and said, oh, well, CH2 protons are actually identical to each other because of rotation around carbon-carbon bonds. They can be in the same environment. And that's generally true, but not in a chiral environment. And this molecule that we've drawn is chiral, and there's a stereocenter. So we're going to look at beta carbon 2, doing a Newman projection. To our right would be the CH3 group. HA would be up, HB would be down. And then in the back would be the alpha carbon that we can't see, with a methyl group opposite on the alpha carbon to where the methyl group is on beta 2. And then up here would be bromine, and then here would be another hydrogen. All right, so you're looking at beta carbon 2 here. Now, looking at this, we've got 2 different protons on the beta carbon, or I've told you they're different. You've got HA and HB. As it is right now, HB is the one that is anti to the leaving group. So if the molecule reacted from this conformation, we would find the base removing HB. These electrons would kick down to form a new pi bond between alpha and beta carbons, and the leaving group would leave. as that happened, we would see both alpha and beta carbons become sp2 hybridized. The methyl group is going to stay on our right. HA is going to stay on our left. There's beta carbon 2. In the back is the alpha carbon. The proton will stay on our right, and the methyl group will stay on our left. And we've just made a trans alkene. And if we look at it from above, then let's see. Sorry, getting distracted. On our left would be HA. And we would have formed this double bond, and we would have gotten the trans product. Now, if we start from this Newman projection and instead rotate the molecule, let's grab a hold of HA and let's rotate counterclockwise by 120 degrees. The carbon in the back is going to stay exactly the same. But what will change is now for the beta carbon in the front, HB is here, methyl is here, and HA is here. So notice the difference between these two conformations. When HB is anti to the bromine, the methyl groups are trans. When HA is anti to the bromine, the methyl groups are on the same side of the molecule. What that means is that HA and HB never experience precisely the same environment. They are never gauche/anti to exactly the same things if you made a list. And that means they are different, always and forever. Now I'm doing Napoleon Dynamite end credit scene. Sorry about that. Nobody knows what I'm even talking about because your generation doesn't watch Napoleon Dynamite. But 20 years ago, it was cool. Whoa, whoa, whoa. Casting aspersions here. Sorry about that. Okay, I'm pleased. I'm proud of you all. The first time I saw that, I think must have been, we were at Amber's house. I think we were pretty newlyweds, and her brothers loved this movie, and you got to see it. And I watched it, and I was like, what the heck is going on? The movie has almost zero plot, and it's stupid, but it's kind of one of those things where if you continue watching it, it becomes fun to quote, and then suddenly you think it's hilarious. So Nacho Libre is much the same way. All right. Successfully derailed the lecture. Where are we now? A and B, always and forever, there it was, are different. We have a word for that. They are called diastereotopic, and they have different environments. I introduced that word because you're going to encounter it, if not in 351 and 352. Certainly those of you that have to go on and take the organic lab, Dr. Bronson is going to continue to hammer that issue that CH2 protons in chiral molecules are different, and you're going to need that in order to solve the NMR spectra of organic compounds. So just put that in the back of your brain. Remember there was something called diastereotopic protons, CH2 groups in a chiral molecule that are not equal to each other. Another way to view this is if we remove the proton here and do the same elimination reaction, we should get, instead of the trans isomer, we should get the cis isomer. Okay, and this is another way you can rationalize why these protons are called diastereotopic, because removing one versus the other generates diastereomers. So we've got three potential products, one for each different kind of beta proton. Blue beta proton leads to monosubstituted alkene. HA purple proton leads to cis disubstituted alkene, and purple proton HB leads to trans disubstituted. I'm misspelling words, but that's okay. Trans disubstituted alkene. Right? So a complete answer to the question, what happens when you do the E2 reaction, what are the products? A complete answer has to include all of the Regio isomers and diastereomers. All right, so if this were an exam question, I asked which of the following are products, and I showed you all kinds of options. You would have to select 1, 2, and 3, but not 4 or 6, unless it's a Thursday, in which case 7. You're not laughing because it's not any fun to answer those questions. So the fact that we've got multiple products allows us to ask a question, is there any way to tell which one would be the major one? And an important observation is that for the E2 reaction, the most stable alkene is the major product. The reason for that, I spent some time, I think, in the first hour talking about why that's the case. It's not a major issue, so it may not be worth spending too much time on. The reason that this is the case is that the E2 transition state resembles an alkene, and therefore the more stable alkene comes from the more stable transition state, which means the more stable alkene forms faster. Which, I'll just add as an aside, that which product forms faster only matters for reactions that are irreversible, that is, are not in equilibrium. And that is really the case for most E2 reactions. If you look at the products, the alcohol, the bromide, and then the alkenes, it's actually quite downhill in energy to go forward here. It would be very difficult to go backwards. So, now, which of the three is the major product? Well, the more stable one. Okay, fine, which is more stable? Let's compare cis versus trans to begin with. What do you think in that comparison, which is the more stable alkene? Trans is more stable than cis because sterics. And we illustrated this in the first hour by looking at Spartan. There is a trans alkene, and the methyl groups are far from each other. You can tell that both in the stick image and in the space-filling image. If in contrast we turn this into a cis alkene, whoops, you might say, what are you talking about? Those methyl groups aren't close to each other. Yes, but remember, atoms have radii, and the methyl groups actually are touching when they're cis to each other. So there's some steric issues associated with the cis alkene that the trans one doesn't have. So if we were thinking cis versus trans, then certainly trans would be major. What about, so that's a stereoisomer issue. What about the Regio issue? What is the more stable connectivity or regiochemistry? That is, if you've got mono versus di-substituted alkenes, which of those is more stable? So there's a rule in your text that says that more substituted alkenes or olefins are more stable. I think they name it after somebody who is dead. So I don't remember what the name is. I always get confused. Might be Zaitsev or something like that, but we don't need to remember that name. You could just memorize the rule. Alternatively, you could explore why the rule is the way it is, and that tends to be a more useful approach. So why would a disubstituted olefin be more stable than a monosubstituted olefin? It's not sterics, and if it's not sterics, it is often hyperconjugation, as in terms of explanations. Hyperconjugation or resonance or some other thing involving electron density. So, hyperconjugation of the pi star, the LUMO of the olefin, and the sigma CH, the carbon-hydrogen sigma bond on the allyl carbon, that is the carbon that is adjacent to the double bond. So the pi star is going to be the empty orbital, and the carbon-hydrogen sigma bond is going to be the filled orbital. Let's go ahead and draw the monosubstituted alkene as though we were looking at it from the side. And I'll draw a carbon-hydrogen bond here, and there's another, and then there's a methyl group. Let's draw the pi star. There's a node in between the two vinyl carbons with lobes on either side. Every time there's a node, you have a change in wave function sign. I'll just fill that in to make our drawing of the pi star complete. Now, before we've dealt with hyperconjugation in a lot of detail, I've described hyperconjugation as this process where you mix the filled sigma bonding orbital with the empty orbital in plus and minus combinations. The filled orbital is usually lower in energy than the empty orbital is. And mixing those two together in the plus combination gives you a lower energy orbital where the electrons get to spread out and but are therefore stabilized, whereas the higher energy orbital the empty orbital ends up moving even higher. This is the minus combination, but who cares because it's empty. And what happens here is that the LUMO spreads out even more. And so in this case, we would expect the carbon-hydrogen bond here to be delocalized a little bit towards the two vinyl carbons, and we'd expect the pi star to move out a little bit onto the adjacent proton. In any case, if you want to just simply remember that hyperconjugation between the filled sigma bond and an empty pi star is stabilizing, then you don't even have to draw the orbitals. You just have to realize that the more adjacent CH, or the more, I'm sorry, maybe I can say this in a different way, the more allyl carbons we have, that is, the more substituted the olefin is, the more favorable and stabilizing sigma to pi star hyperconjugation can occur. All right, so more substituted olefins are more stable because if you compare the di versus the monosubstituted only has one allyl carbon with bonds that can hyperconjugate with the pi star, whereas the disubstituted has two, just more opportunities for stabilization. Okay, any questions you want to ask about that? So if we put 2 and 2 together, we know that the disubstituted products are more stable than the monosubstituted products, and that trans is more stable than cis. So we could call trans the major product and the mono the minor product. Last hour, some students asked, would I expect you to rank these 1, 2, and 3? Probably not. Whenever I ask which is the major product of this reaction, there will always be a clear choice. Same with which is the minor product. In other cases, I might just have you draw all of the products for a reaction, or rather select all of the products for a given reaction. All right, so those are the regio and stereochemical issues associated with the E2 reaction. What else do we need to say? Getting ahead of myself, so I need to remember what I told your compatriots. Unless you want different things than them. Somebody asked an interesting question in the first hour, and that was, what if I have more than one leaving group in the molecule? Are there cases where I could form some interesting products? And so what I'm going to show you is a preview of something that you'll encounter later. The preview is that you could take an olefin, an alkene, and you could add bromine to it, and you could get the following dibromide, where you have bromines on 2 adjacent carbons. That is a chapter 10 reaction. We call this molecule where bromines are on adjacent carbons a vicinal dibromide. Vicinal stands for neighbor, and Spanish speakers may recognize familiar letters there. Vecino, I think, is my properly Americanized pronunciation of that Spanish word. If you provide one equivalent of a strong base, what do I mean by equivalent? I mean 1 mole of strong base for every mole of starting material, vicinal dibromide. You can do an elimination reaction of 1 of the 2 bromines and 1 of the 2 protons. And then if you add a second equivalent of a strong base, you can actually do a second elimination reaction to make an alkyne. The base that's typically used for this reaction is a really strong base that is not a good nucleophile because of poor solubility. It's a tremendously sterically hindered base because it exists as a macroscopic chunk at the bottom of your reaction vessel. So it's a terrible nucleophile, but it's a decent base. And this is one of the ways you can make alkynes, which are involved in chapter 11. So anyway, that's an interesting pathway that I told your predecessors about, and I call this tandem E2 elimination because you have one E2 reaction followed by the other. What other questions? Yeah.
I'm still just a little confused on how there's more opportunity for hyperconjugation between the mono and the di.
Okay. So why is there more opportunities for hyperconjugation for mono versus di? Notice here's a monosubstituted olefin, and none of these hydrogens on the vinyl carbons can line up with the pi star, so they just can't do anything. Though if we here, the one non-hydrogen thing has carbon, hydrogen, and carbon-carbon bonds that could line up with the pi star and do hyperconjugation. The more of these vinyl protons we replace with hydrocarbon things, the more adjacent CH bonds we're going to have, and that means more chances for hyperconjugation.
Thank you.
Yeah, so that would be just like, now we have 2 instead of just 1. And the more, and we could add others and stability would continue to increase. Other questions? Yeah?
If you were to compare the cis with the monosubstituted one, which would be more stable because then it would be like hyperconjugation versus
Yeah, so the question here in the classroom is, if you compared cis versus the monosubstituted, does the increased opportunity for hyperconjugation compensate for the steric repulsion between methyl groups that does not happen in the monosubstituted isomer? The answer is I don't know. So what we want to do is develop some sensible predictions, and then as reality differs from what you predict, you can at least understand what issues might be interesting to study as scientists. In this case, we would expect the trans to be the major and the minor to be the monosubstituted, though if you did observe more of this mono than the cis, then maybe you would say, oh, probably sterics don't compensate totally for hyperconjugation. What I would expect on an exam is for you to just make the prediction that the trans is more stable than the cis, and the minor is, and the monosubstituted is less stable than the disubstituted ones. Yeah. Good. Other questions? Okay. Well, let's see how well you understand these stereo and regiochemical issues. I'm going to draw a product. This may come from your practice exam. I don't know. So we may be ruining something for you. If so, I apologize. Fine. All right, let's say I want this product. pH, by the way, with a capital P and a lowercase h, stands for a benzene ring attached to something, a phenyl group. And so sometimes rather than drawing out a whole benzene ring, I will just abbreviate it. In this case, it doesn't really matter. These are sort of just placeholders for us. But suppose I want this desired product and I want no other stereoisomers, and I also want no alternative regioisomers. And suppose that I want you to make this via an E2 reaction, and I need you to design a starting material that would lead in an E2 reaction to exclusively that product. All right? Remember that an E2 reaction is elimination, and which means that the alpha carbon had a bromine, the beta carbon had a hydrogen. We basically lose a hydrogen and Br minus and make a new pi bond. So if you look at the pi bond in our product, maybe we'll number those 1 and 2. One of those is going to have the bromine, the other is going to have the hydrogen. So we can try out both connectivity patterns and explore whether one of them is more promising than another. Let's put the bromine on carbon 1, and let's put the hydrogen on carbon 2. And let's look at that and see what problems we might anticipate. And then let's consider the other option, where instead we put the bromine on carbon 2 and we put the proton on carbon 1. All right. So let's explore regio and stereochemical options. Looking at option number 1 versus option 2, do you see any problems with, let's say, option 1? Let's consider that first. Any issues? Go ahead.
There are a lot of steric interactions on option 1. There are not really big groups, so the other one would probably be more stable.
Okay, so you're looking at option 1. What steric issues do you see for 1 that are not present on 2?
But just on the left, we've got 3 really large groups. whereas
1,
on the-
2, okay. All right, so you're concerned about having the bromine here next to methyl and phenyl versus just here next to phenyl. Okay, so there may be some conformational stability issues, which is a more stable conformation. I actually hadn't thought of that, and I think it's a good idea to think about that. If we look at A values, which give us a sense for how big things are, hydrogen's A value is 0, bromine's A value is, I'm going to forget, but it's something like 0.38 or something. So bromine is not as big as a methyl group. You are right, it probably is maybe more stable to have it here than there, but it maybe isn't a huge issue. In terms of regioselectivity, what do you see? Or stereoselectivity? Yeah.
Can't we not really observe until we have which ones are coming in and which ones are coming out?
Okay, so Hannah here in class is asking, well, come on, you don't actually maybe know whether there's going to be stereochemical issues or not until I know what's up and what's down. Okay, fair enough. But even without knowing that, there's a regiochemical issue.
Is that answer you should have?
There's an answer. The hydrogens could rotate around the single bond, giving us trans and cis. Okay. Yeah, so Richard at home is noting that if I've got these 2 hydrogens on beta carbon 2, if I eliminate one of them, I don't right now know which is up or down relative to bromine, whether it's up or down, but by analogy to the example we did previously, I know that if I have 2 diastereotopic protons adjacent to a leaving group, one will give me one stereoisomer and the other will give me the other stereoisomer. So yeah, right here you've got the potential for 2 diastereomers to form, independent of what, where the bromine is. All right, there's another problem, and it has to do with this methyl group. And the moral of the story here is beware the hidden beta proton. I wrote that as a CH3 group so you would ignore it. And in doing so, I deceived you because that is also, oops, why am I scribbling it out? That is also a beta proton. This is a situation like we had earlier. This is beta proton, why am I choosing that color? Sorry, this is beta proton 2. This will be beta proton 1. What is going on? There we go. So we've got the same regiochemical issue. If I remove the beta proton that's adjacent to the bromo group on carbon 1, I'm going to have a double bond between CH2 and carbon 1 instead of a double bond between 1 and 2. In other words, eliminating from here is going to give me this strange product that we don't want. This is the undesired regioisomer. Okay, so moral of the story, look for multiple different kinds of beta protons. That's going to help you in predicting products because each different kind of beta proton will lead to a different product. In a synthesis, or when you're thinking backwards about what starting material would lead to this product, looking for the different kinds of beta protons will help you see what your options are. So let's examine option 2, to see whether we've got any similar issues. Carbon 2 is our alpha carbon, and it may help at this stage to draw out the phenyl group. How many beta carbons do I have? Well, I've got one here, and I've got one there. Both of those are beta carbons, but no protons on the other beta carbon. So I only have one beta proton here. And so that's good, because that means I have a chance, only one beta proton, that means I have a chance of getting only one product. Now, we got to deal with getting the right product. We're going to get the right connectivity here, but the question is, we don't just want the right connectivity, we want the phenyl groups to be cis to each other and not trans to each other. So this is going to require us to think through what is where when hydrogen is anti to the leaving group. So you can do this in multiple ways. One simple way to do it might be to look at, to draw a Newman projection and just start out with the assumption that carbon 1's in the front and carbon 2's in the back, and we're going to put the proton on carbon 1 up and the bromo group on carbon 2 down so that they are anti to each other. And now on the front carbon, I need to fill things in, and actually I can make whatever choice I want. I could put phenyl here and methyl there. If I want to end up with this option where the phenyl groups are on the same side of the molecule, on the back carbon, where should my phenyl group go? Left or right in the Newman projection? Got two options. So I'm hearing a Beyonce song in my head about people being irreplaceable and being pushed off to the left. So yes, that's, if we arrange it this way, then the beta proton that is adjacent to the leaving group, those are anti to each other. The two things that we need to be cis to each other in the alkene product are gauche to each other in the precursor, so that when a base removes the proton, we make the new double bond. In the final alkene that we form, the two phenyl groups will be cis to each other. Now that we've done that from a Newman projection point of view, if you like, we can take the same starting material and go through the process sideways. No, there we go. I thought I copied something, but apparently I didn't. Now, at this point, it would have taken me less time to just draw the dang thing. All right, so I've already arranged things such that hydrogen and bromo are anti to each other. So I could make a choice here to put the phenyl group out and the methyl group inward or towards the page. If I'm going to do that and I want to end up with the cis product, I would have the phenyl group on carbon 2 pointing out at me as well. All right. One question you could ask, though, is what if I chose instead, over on carbon 1, you remember as I was filling in dashes and wedges just now, I chose to have phenyl coming out at us. What if I put phenyl going back into the page. What, is there still a way for me to get to the desired cis alkene product? There is a way. So what is it? Is there something I can change about carbon 2 that would make it so that it works? Hi, is this Air 5 with Hannah? Yes. I think you meant what? Push the phenyl group back into the page?
I meant air high five.
You meant Air high 5. That's good. I like Air 5s. Yeah, so if we go from this stereoisomer, the H and the Br are anti to each other. Notice that the phenyl and the phenyl are on the same side of the molecule, so they're going to lead to this product too when we do the E2 reaction. Fun remedial exam 2 work. What is the relationship between these two compounds? They are enantiomers. They have opposite configuration at both stereocenters. This is why we say enantiomers have this. This is one of the evidences that enantiomers have the same chemical and physical properties, because if you're going to make an achiral product out of the enantiomer, both of them will lead to it. Right? You got a couple of options there. Okay. And now that I'm thinking about it, I would hesitate to generalize too much. The only reason this works is because of the requirement that the hydrogen be anti to the leaving group. And in that case, it just so happens that both enantiomers preserve the relative stereochemical relationships between these groups. That is, both of them have the phenols on the same side of the molecule. All right. So that's maybe as complicated as stereochemical issues of the E2 reaction get, but that's worth some practice because you can bet if I gave you this starting material, you can bet I would put among the various options both stereoisomers and perhaps some other regioisomers, and you would need to predict the correct ones or select multiple options if they were accurate. So you've got to be able to follow through the stereochemical information in the starting material with what ends up in the product. That gets us to exactly where we needed to get with respect to your compatriots in the other class. So I think we're going to go ahead and leave it there. Friday, we got a few more things to talk about E1. And then we're going to put it all together in terms of predicting what happens where when you just give an alkyl halide and a particular nucleophile or base. All right, so see you next time. Yeah, Sierra, the rule is for an elimination reaction to happen, the beta proton must be anti to the leaving group.